Welcome to our next segment of Chemistry Tales. We are giving consideration to atoms and the subatomic particles that exist in atoms. And our next section is going to deal with ions. We're also going to review a little bit of history and where these discoveries regarding subatomic particles comes from. And then lastly, in this chapter, we're going to review molecular structure and the mass percent of elements in different compounds. Okay, so to begin, what is an ion? Okay, ions are atoms, or possibly a group of atoms that are bonded together that have either gained or potentially lost one or more electrons. Okay? So we wish to review predicting the symbol for ions, whether it's a positively charged cation or a negatively charged anion. And then we're also going to review predicting the number of protons, neutrons, and electrons in an ion. Let's start with cations. Okay, a cation is positively charged. Okay, it's positively charged because it has lost one or more electrons. Okay, for example, in general, if I have some element X, that's a neutral atom, and if it loses an electron, it's going to form a +1 charge. If it loses 2 electrons, it's going to form a +2 charge. Okay, so those are examples of cations. So the element sodium, if it loses 1 electron, it forms the sodium ion. Okay, so, and if you look at aluminum, okay, it likes to lose 3 electrons, and so it's going to form a +3 cation. So let's summarize the number of protons and electrons within the ions that we've just looked at. Okay, starting with the sodium atom. Okay, sodium's element number 11, so it has 11 protons, and the neutral atom has 11 electrons. But if we take away 1 electron, now it has 10. So the sodium ion has 10 electrons. Aluminum is element number 13. It has 13 protons and 13 electrons. But if we take away 3 electrons, the aluminum ion is going to have 10 electrons. All right, and the complement of a cation is an anion. These are our negatively charged particles, and they are the ones that are going to be formed when a neutral atom gains 1 or more electrons. Okay, so now let's review a potential anion. So the element fluorine likes to gain 1 electron and form the fluoride ion. That is an anion. We'll go through naming conventions a little later, but when you form the anion, it has an IDE ending compared to the element name. Oxygen likes to gain 2 electrons, so it's going to form the oxide 2- anion. Okay, so these are examples of our negatively charged anion species, and we want to predict the number of protons and electrons within our anions. Okay, so for fluorine, we're going to start with oxygen. Atomic number 8 has 8 protons and 8 electrons in the neutral atom, and I gain 2, so oxygen's going to have 10 electrons. Okay, nitrogen likes to gain 3 electrons. It would form the nitride, IDE ending, anion. Okay, and so if we predict the number of protons and electrons, this is element number 7. So the neutral atom, 7 protons, 7 electrons, but the anion has 10 electrons. Okay, so this is a quick review of our positively charged particles and negatively charged particles. And I just want to remind you that many of our ions are what we call polyatomic ions. They are a group of atoms that are bonded to each other that have collectively gained or lost one or more electrons. Okay, so at some point you're going to have to go back and review predicting the structure, charge, and names of your polyatomic ions. So for example, the nitrate ion is NO3, and that group of atoms carries a -1 charge. The carbonate ion, CO3 2-. Okay, and there are some polyatomic cations, such as the ammonium cation, NH4 carries a +1 charge. So I'm just kind of giving you a little heads up that at some point in the future, you're going to have to remember the structure, charge, and names of your polyatomic ions. Okay, so what we're going to do next is just try to give credit regarding the scientists who made the major discoveries that led to our understanding of the atom and the subatomic particles. So let's start with the electron. Okay, who discovered the electron? Well, basically that was the work of J.J. Thomson. This was back in the 1906. He won the Nobel Prize for this. Anyway, so his experiment involved a gas discharge tube, so a tube that was evacuated of all gases with the exception of helium. And then within that tube there were terminals, electrical terminals, okay, an anode and a cathode. The anode is the negatively charged terminal and the cathode is a positively charged terminal. I'm missing an H in my word cathode there, sorry. He also used a magnetic field. Okay, so there was a B field, as it's called, and basically what he did in his experiment was he applied an electrical potential between the two terminals. Okay, this caused some kind of change to the helium atoms. And what he observed is there was a particle beam that was being released from the helium atoms. And what he observed experimentally was that when he moved the magnetic field, it would deflect the particle beam. Okay, so what this tells a scientist is that those particles being emitted by the helium atom had charge. They were charged. Okay. The other observation was that this particle beam being released by the helium atoms was attracted to the positive terminal. So physics tells us that opposite charges attract. So whatever was being released by the helium atom had to have been negatively charged. So in essence, he observed that these helium atoms exposed to an electrical field were forming a species, positively charged species, and particles known as the electron. The big contribution of Thomson was the measurement of the charge to mass ratio of the electron. He measured this to be 1.759 times 10 to the 8th, and the units are coulombs per gram. So very cool experiment, and that's how science works. Okay, so science progresses over time, and teachers hopefully impart knowledge to their students. And so historically, once the discovery of the electron was made by Thomson, then his student Millikan went on to do further experiments and discovered the charge of the electron and the mass of the electron. So in 1909, centuries ago, literally, Millikan did a famous, what was known as an oil drop experiment, in which he suspended drops of oil that had these electrons in them, and he measured the potential at which electrical potential between two terminals, the voltage, that's the same thing, the electrical potential. He measured the voltage required to suspend these oil drops containing these electrons between the two terminals. And physics tells us that if an object is stable, there are forces acting on it, and the magnitude of those forces are equal and opposite. So there was a gravitational force pulling on that oil drop, and then there was this electrical force that he applied. And so, long story short, from that data and those observations regarding the magnitude of the voltage, he was able to determine the charge on the electron. Very cool. And that value is 1.602 times 10 to the negative 19th units or coulombs. So he's got the charge on the electron, okay? And then coupled with the information from Thomson, which was the charge to mass ratio, if you take the charge of the electron and divide by the charge to mass ratio, you get the mass of the electron. Really neat. So I'm going to show you here plugging in the values that both of these scientists were able to derive through experimental data. The charge is the 1.602 times 10 negative 9 coulombs. The charge to mass ratio discovered by Thomson, going into the denominator here, 1.759 times 10 to the 8 coulombs per gram, is going to give unto us the actual mass of the electron, okay? And so the 9.1 times 10 negative 28 grams. And so that is where that data came from. So once again, this is science at work. You design experiments, you record observations and data, and then you come up with theories in which you can explain that data. Okay, so historically, we know we have electrons, we know their mass, we know their charge. So who gets credit for discovering the atomic nucleus, the protons, the positively charged particles within the nucleus? That credit goes to a scientist by the name of Rutherford. And Rutherford did a famous backscattering experiment with what he discovered as alpha particles. So before Rutherford, we knew we had electrons and protons, and at that time, the model of the atom was that these negatively charged particles and positively charged particles were kind of distributed randomly throughout the atom. That was known as the plum pudding model, okay? And it explained the data that they had discovered thus far, okay? But Rutherford went on to do this famous backscattering experiment, and his observations could not be explained by the plum pudding model, so he had to come up with a new model. Okay, he discovered the nucleus, the existence of a small region of space at the center of the atom in which the positively charged protons existed. So what did Rutherford do in his experiment? Well, he used helium ions with +2 charge. Those are called alpha particles, 2 protons, no electrons. Okay, so he fired a beam of these alpha particles that had the +2 charge. He fired those at a thin film of gold atoms, right? So if the plum pudding model existed, you would expect to see deflection off of the electrons in all directions. But what actually was observed is that the beam came back almost entirely back at the original direction of the source of the alpha particles, the positively charged particles. So that was very, very unexpected, this severe deflection. And so what Rutherford had to come up with as a conclusion was that the positively charged particles within the gold atoms were constrained to to a very small region of space. The severe repulsion of the positive alpha particles by those regions of space in the atom that had all the protons, the positive charge. So anyway, so very cool experiment. And so he had to come up with a new model of the atom which would explain this severe deflection of these alpha particles, and thus this is what we call the nuclear model of the atom, in which we believe that all of the protons that have the positive charge reside in a very tiny region of space at the center of the atom, and that the electrons exist outside of that region of space within the body of the atom. Okay, and so here's a nice little quick diagram of the nuclear model of the atom. So there's the atom, and at the very center of the atom is going to be our nucleus. The nucleus is going to contain all of the protons of the atom. Later on, other scientists are going to discover the neutron, but at the time of Rutherford, you know, he was the main one who gets credit for the existence of all the protons existing in that small space at the center of the atom. So it's time to use the left side of our brain and look at the artwork outside of the chemistry building. Here's a picture of Annie standing on one of the half atoms. So she's standing where the nucleus should be. If you didn't already recognize the artwork outside of the chemistry building, the black granite spheres are supposed to represent atoms, and the etches in between are the attractive forces between atoms, and this is supposed to be water in the gaseous phase. As you transition into the chemistry building, the floor is water in the liquid phase. So the chemistry building, as you enter, it's a metaphor for the transformational powers of education, going from the gaseous phase to the liquid phase to the solid phase. So there's your history on the artwork of the chemistry building. Okay, and to complete our story about our current understanding of the atom and its subatomic particles, we need to kind of go back and give credit to the scientists who discovered the neutron, and this is going to lead us to information in the next chapter regarding electrons and how they're organized in the atom. But after the work of Rutherford, we had an understanding of the atom in which we have a nucleus, and all the protons, all the positively charged protons are in this small region of space at the center of the atom. Okay, and just a quick reminder, protons are all positively charged, and physics tells us that like charges repel each other. So there should be some instability with having all those positive charges in a tiny, tiny region of space. And so experiments had to be done to help explain why a nucleus is stable, okay? Why those particles don't fly apart. So the radius of an atom in general is on the order of 1 angstrom, which is 10 to the negative 10th meters. And the size of the nucleus, the region of space where all the protons were, was on the order of 10 to the negative 5th angstroms. So tiny, tiny, tiny region of space at the center of the atom. So a collection of scientists were able to design experiments that helped to explain why a nucleus is stable and those positive charges don't repel each other and fall apart. Okay, so this is the work of the scientists Both, Becker, and James Chadwick about 1930. They discovered these other subatomic particles which are known as neutrons, which are neutral particles, and basically their function in the nucleus is simply to get in between those positively charged protons that are repelling each other and to dilute them, okay, to make the nucleus stable. And if you look at the elements in the periodic table, as we get to bigger and bigger atomic numbers where we're shoving more and more protons into the nucleus, the relative proportion of neutrons to the protons goes way up, because the more of those positive charges we pack in there, we need to dilute them significantly. Okay, very cool. So this is the kind of collective history of our understanding of the subatomic particles. And so what's left is to have a detailed understanding of the electrons outside of the nucleus. How are they organized? And so this is leading into the topic of quantum mechanics, which basically is the coverage of material in Chapter 3, in which we're going to understand the energy relationship of the electrons. Quantum mechanics is a study of the energy affiliated with our subatomic particles and helps us understand properties of atoms and behavior of atoms. So this is leading into material coming up in Chapter 3, electrons, orbitals, all that good stuff. So I think it's just really important to lay a solid foundation for our understanding of the subatomic particles and the behavior that they exhibit within atoms.